Anyhow, sorry for those of you, I forgot to record, so you can hear this real quick again. New homework's up. Let's just remind ourselves of what the definition of probability is in the classical sense. And then we need to remind ourselves of why this definition has some issues. And there's more than just these two, but these are the two ones that should be obvious to us. Maybe not obvious to you, that's unfair, but if you think about it, they might be obvious to you. And then, so how are we going to fix this? Well, we're gonna try to fix these issues by first developing an axiomatic approach to probability, and it's gonna use some deep math ideas. And then the second thing we're gonna do when the time is right is we're gonna study what we say is basic combinatorics. And these are, you could think of this as a fancy word for counting. But you can Google it if you want. You might learn some things. All right. Does anybody have a comment, question? Okay, so here we go. So what we're going to do is we start by assuming what we call axioms. Axioms are basically, you can think of these as rules. These are rules to the game. You guys may be familiar with the word axiom. I would assume in high school you took a class in geometry and you would have studied basic, what we call Euclidean geometry. And you study these, there's these 5 axioms and 5 postulates. Axiom is basically like, here's the rules we're going to set up. Okay, so what are these axioms? Well, we're going to list them. Number 1, if E is any event, then the probability that E occurs must be some number between 0 and 1. A cool thing to think about with this is, again, I'm not defining what probability is. There's no formula right now. It turns out that that formula that we gave you, the classical probability, it can be deduced from these axioms. It can be logically sort of proven, as we say. But basically what we're telling you is the probability of any event has to be a number between 0 and 1. And that's not a bad thing. You guys know that any number between 0 and 1 can be written as a percentage, right? So then your ideas of things like, oh, okay, cool, there's a 37% chance it rains. Well, we can still have this sort of intuitive notion of likelihood. Okay, so that's our first rule. Now, again, I'm going to go slow here because it's important you understand why we're doing this. We want to develop a sort of notion of probability that agrees with our intuition. And right now, this agrees with what we had before. In our definition of classical probability, it was a number divided by another number. And the sample space was always going to have more elements than the event, so it was always a fraction, which means it was always a number between 0 and 1. So this is in agreement with our classical definition so far. Okay, now, this is where the fun sort of begins. You're not allowed to get nervous when I write the next couple things down, all right? This is... All right. The next thing is if S is the sample space, the probability of S equals 1. Now, this is a fancy way of writing something, so it's nice to write this in English so that you have an understanding of what we're doing here. Basically, this says at least one of the outcomes must occur. So this tells us at least one outcome will occur. So if you want to, that's the fancy way in math is saying that the probability of the sample space is equal to 1. That means at least one outcome will occur. And we get this. If I'm flipping a coin, we know that it's either going to be heads or tails. If I'm rolling a pair of dice, I know I'm going to roll a number between 2 and 12. And we're ignoring the fact that it might roll on its side, right? If I am applying for a loan and the bank gives me a loan, I will either pay it back or I will not pay it back. One of those will occur. Right? All right, now here's the one that's usually very scary as well for students, and this is the following. So, and basically because of your limited mathematical exposure, this is even more scary. So if E sub 1, oh boy, E sub 2, E sub 3, and this goes on and on and on, are events. Now we're going to stay a phrase here that we're going to have to define. That are mutually exclusive. Then the probability that E sub 1, now we're going to use a math symbol you might not have seen before. And don't stress about this right now. It's not the end of the world. We're going to explain what this means in a second. If you've ever had calculus, this might make a little more sense. If you haven't, do not worry about it. So before I go to the next page, there's a couple things I want to say about this. What does mutually exclusive mean? We didn't define it yet, but here's what it means. It means they both can't happen at the same time. A heads and a tails are mutually exclusive. So think about what you know about the English word exclusive. If I'm rolling a pair of dice once, I can't roll a 7 and a 9. So those events can't occur at the same time. But there are events that could occur at the same time. If I'm rolling a pair of dice, I can roll a 5 and I can also roll an odd number. But the event of rolling a 5 and an even is not the same. Do we understand that? Now, another thing that's going to be difficult for most of us is, what is this little U-like symbol? We haven't showed you sort of what that is yet. Now, some of you may have seen it in another class, and if you have, that's great. And we're going to explain sort of what that is in a second. Does anybody have a question about this first? So let's sort of make sense of this third one. So this guy needs explained. So let's say events A and B are said to be mutually exclusive if they can't happen at the same time. So real quick, let's look at this in terms of examples. So a coin is flipped. Heads and tails are mutually exclusive. A die is rolled. Rolling a 5 and an even number are mutually exclusive. So the event of rolling a 5 and the event of rolling an even number can't happen at the same time. However, if I said rolling an odd and a 5, that could happen at the same time. Now, one of the things you're going to learn is that if the way I'm teaching this is different than how the book does it, and that's okay, you're going to see two different presentations. That's actually, in my opinion, better than me reciting what the book does anyhow. The book uses 4 axioms, and they don't write them the same as mine. They are technically the same. It's just we're writing them differently. Okay, so in math, we use the following symbols. And this is where you're going to see from 2 pages ago. So remember, and this goes back to how much sort of math you might remember from previous courses, and I'm not going to assume you remember any of this. But if we say a sample space is the set of all outcomes, in math, we call that a set. Now, you're used to seeing sets of numbers. You've seen them before. You were asked as a student of, these are the natural numbers, these are the integers, or these are the negative numbers, these are the even numbers, these are the odd numbers. You've seen sets of numbers before. You've seen intervals for sure in like an algebra class. And so we have certain notations that we do that we use in these situations to tell the reader if something is in one set or the other. And you may have seen this before, you may haven't, but it's worth at least exposing it to you. And hopefully it'll become sort of something you're capable of dealing with. So if we have 2 sets, or in this case, 2 events, A and B, we can ask about 2 new events. The first one would be A and B. And the second one would be A or B. So think about this. Let's put it in a phrase of a problem. Let's think of a deck of cards. I can say, everybody here is familiar with a deck of cards. I can say, I'm going to pull 1 card from random. There's 52 cards. I might ask, what is the probability I pull a club and an ace? Well, how many options are there for that? Well, there's only 1 ace of clubs, so there's 1 option for that. And so that is different from the probability of me asking, what if I pull a club or an ace? Well, now I have a lot more options because there's 13 clubs and there's 4 aces. Now, of course, one of those aces is in fact a club, so I can subtract that away, but you see that I have now what? 16 options. Does that make sense? So we have math symbols for this that you might see. In symbols we write A, and then we use this upside down U. And then here in symbols, you may have seen this in a math class as well. With intervals, we write AU. So let's sort of tell you what these things mean. So this is called a union symbol. And the upside down one is called an intersection symbol. Now, you've likely not seen these defined, but you may have seen them. I would imagine some of you had an algebra teacher, or maybe you took a pre-calculus class where you've probably seen the union one before. Because we typically, when we're writing domains of functions, you might have seen that before. Now, don't get overwhelmed with this notation. I ain't going to quiz you on it. I ain't going to say, what does this mean? I'm putting it out here so that you're exposed to it. Now, your book doesn't use these symbols. I don't believe they do, at least. They probably use the English words, and or. I don't care what you use. I'm just telling you, because if you're anything like me, and maybe you're not, but the first thing I do when I don't understand something is I go to the internet and I try to learn. And what happens when you start Googling things about probability is you're going to start seeing some scary crap real quick. So I'm just trying to let you see some symbols that you're going to maybe see a bunch of. Okay. So the way I'd like you to think about A and B as being events is think of them as drawers. You have one drawer that has all these outcomes in it. You have another drawer that has all the, or maybe boxes is a better way of thinking about it. Now, maybe you might have, okay, and then you might have a box that has no outcomes in it. So it's empty, right? And so we sort of give that a name as well. And this seems like a silly thing to say, but we have to do it. So if an event is impossible, we denote by this symbol, which you probably have never seen before, but so if any of you have seen this before, maybe you may have heard it. I don't care if you have or haven't. I'm telling you this for your own benefit. So there's a name for this in math. This is called the empty set. So what is an impossible event? Well, let's go back to the cards. What's an impossible event? If you draw one card, it is impossible you draw a red and a black card, correct? So we say, since that's an impossible event, we denote it with this symbol, which is called the empty set. There's nothing in it. It's the box that has nothing in it. This is a mind F, I know. So math is fun. You get to learn all this stuff. Okay, now, again, don't forget that what we're doing here is we're still trying to explain what this third thing means. The first two seem intuitive to us, right? If we're gonna define likelihood, let's make it have to be between 0 and 1 so we can use percentages. And then if we're gonna have any experiment where we define likelihood, it better be that something happens. I mean, just think of real world examples. It either rains or it doesn't. One of those things has to occur, right? You throw a coin in the air, either heads or tails. Now, don't give me this bull crap, what if it lands on its side? Let's ignore that for a second, right? I guess you can maybe get a coin that, on the rarest of occasions, that happens, although I doubt it. Did you guys ever play that game in school? We used to play it in the lunchroom. We're immature guys, and you spin a quarter, and then you have to stop it with your finger, and whoever messes it up, then they have to put their knuckles down. We called it bloody knuckles, and you fired a quarter at their knuckles, and so you could last. Did you guys do this in growing up, or is this just me? The bloody knuckles?
Yeah, we played it at our high school.
Dude, that's good. That's good.
Yeah, they got suspended for it.
You just really?
Yeah.
That's terrible. Why would they suspend? You know what they took? You know, I was smart. In 6th grade, we had in-school suspension. In middle school, and the best thing about in-school suspension was the only room in the whole school that had air conditioning. So what you wanted to do is you wanted to get put in the in-school suspension. And it also, and I shouldn't say this out loud because it's very inappropriate, but there was always like the young, nice, attractive teachers who would be in charge of in-school suspension. So that was where you wanted to go as a 12-year-old boy. So we used to play this game where you'd go up behind someone with a pencil and you go, wow. Because remember, we used to pencil fight back when pencils were a thing. I don't even know if they are anymore. And then we got this idea, if you snap it on someone's neck, it'd be fun because you're immature. And you'd go around doing that. Now we get you an in-school suspension and air conditioning with the nice teachers. Anyhow, back to math. See what you learn with me? This is incredible. And we're sitting here using Kolmogorov's 3 axioms, blowing your freaking mind, and now we're talking about getting suspended in school. I never understood suspension. It was like you're giving bad kids what they want. Right? If they don't want to be there, they're going to act like jerks, and then they're going to leave. Yeah, right? Is this not what happens? And then you're like, Mom, I got suspended. And she's like, oh, it's okay, Stacy. Let's go get our nails done. And you're like, all right. It's like a total FU, the whole system, right? Oh, man. Don't get me started on that. But anyhow, back to math. So we're telling you what mutually exclusive means. So we told you what it means for 2 things to be mutually exclusive. Now, what does it mean if I have notice that I have this ellipse here, that means, as you guys know, when we put an ellipse, that means, well, what is he doing? He has event 1, event 2, event 3. That's the way you should think about this. Why is it? O'Grady's telling us it's possible it never ends, and that's true. Let's think of a game where it's possible it can go on for a long, long time. Let's play the game where I'm going to keep flipping a coin until I get 3 heads in a row. Well, I have no idea how long that'll take. I have a guess how long it'll take, but I don't know. So I guess in theory, it might last forever. Or maybe I'm building some product and I don't know how long my product's going to last. Maybe I'm building a chip for a computer, a processor. There could be the event, it lasts 1 month, it lasts 2 months, it lasts 3 months, it lasts 4 months. I don't know, right? But those are all mutually exclusive. You either last 1 month or 2 months or 3 months. Do you understand what I'm saying? So we have to, if our theory of probability, if our rules are going to allow us to study all kinds of different problems, then it must be that we can talk about events that keep going. So one way I can get you to think about this bottom line that looks real scary is that we're saying that, imagine event E sub 1 means, all right, I made a computer chip, and event 1 is it breaks the 1st month. Event 2 is it breaks the 2nd month, the 3rd, the 4th, the 5th, and then it goes all past 12 into the 2nd year, and then 24, the 2nd year, the 3rd year, 4th year, etc. What we're saying is the probability that it breaks in any given month, all those probabilities have to add up to the total thing. Does that make sense? No matter when it ends. So this 3rd piece allows us to make sense of that. So here's what I'm saying. It might be, let's assume it breaks in the 27th month, right? So somewhere between 2 and 3 years it breaks. And then we test another chip and it breaks in the 26th month, right? Or whatever. And we start to get an idea of how long these things last. Well, what this 3rd sort of axiom tells us is it tells us if we're going to assign any probabilities to how long we think a chip's going to last, it must be that when I add up all those events, they have to sum to the probability of each event. Now, of course, this is going to sound way, way more difficult, but let's assume, let's dumb it down now. What is the 3rd axiom actually saying? Let's start with the simplest example. What's it saying? Let's flip a coin once. How many outcomes are there? 2, heads or tails. What is this saying? It's saying the probability you get a head or tails is equal to the probability of what? The probability of head plus tails, right? Which is in this case what? 1. One of them has to happen. Think about this. Don't overwhelm it. If maybe I'll think about it. Let's look at it this way. Let's try to look at a simple example. So axiom 3 is best understood using basic examples. So let's play a game. Let's do a coin flipped 2 times. So let's remind you of what the sample space is. It's heads, 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 tails, tails, heads, tails, tails. Now let's think of two different events that can occur that are mutually exclusive. How about two heads and two tails? Those are two mutually exclusive events. So let's write this down. On one hand, what is the probability that I get two heads or two tails? Well, if we just use basic rules, that is 2 out of 4, which is a half. Why am I saying that? Because that is the case that I had two heads is one of those, and then two tails is, how many out of the total 4 do those constitute? 2 of the 4. Now, what if I did it the other way? What's the probability of two heads plus the probability of two tails? Well, the probability of two heads is 1/2. What's the probability of two tails? Excuse me, 1/4. What's the probability of two tails? That's 1/4, and that also adds up to 2/4, which is 1/2. So the point is no matter how I compute it, I get the same number. That's what the third axiom is telling us. So of course you're going to say, well, Grady, if it's this kind of easy to understand, why did you write it with these scary symbols over here? Because we need these scary symbols if we want to be able to study all kinds of different things that we encounter in the real world, not just flipping a coin. Is this maybe sort of understood? So even though this looks scary to you right now, I get it. It looks scary to me now. And hell, I've been doing it for years. No, it doesn't really look scary to me. I get it. But the point of the matter is we can think of an experiment that we don't know exactly when it's going to end. If I say we flip a coin 3 times, I know exactly when the experiment ends. But there are other games where we could say, okay, I'm going to play experiment. I'm going to, you know, me and Amy are going to go home and I'm going to flip a coin and she's going to flip a coin. And every time she gets a heads, I pay her $1. And then we go until I don't have any money left. Well, I don't know how long that's going to take, at least in the beginning. So I have to incorporate that I don't know how long that's going to take. And so that's why we have these ellipses here. Does anybody have a comment or a question? Now, I got to be honest, most of the things we're going to talk about aren't going to be this scary. Let's do another example where this third axiom sort of comes into play. Let's do another one. So a pair of dice are thrown or rolled. I'm not going to draw out the sample space again, but let's do that thing I've yelled about. Let's take the probability we roll a 3 and, or excuse me, not and, or we roll an even. Well, of course, what are all the chances that we can roll a 3? You had a question. Did I write something wrong?
No.
Can you read that?
Yeah.
Is that green okay? I feel like it might not be good. It's kind of... So you might have to fill in the details of this, but what's the probability we roll 3? How many of those are there? No, because I'm rolling a pair of dice. So I can get a 1 and a 2 and a 1, right? So there's 2 times I can get a 3. Now, how do I get an even? That's a little more difficult, right? But we don't have to know that, because the third axiom tells us that this is the same as the probability of a 3 plus the probability of an even. And what's the probability of a 3? We just told you that's 2 out of 36. What's the probability of an even? Well, that's a little more difficult, right? You might actually have to Google your little sample space again to understand that. So let's do that. Let's kind of show you what we mean by that. So if I go to the internet and I'm going to go to dice sample space. I think you can just do that, Google search. Go to images. Here's the one we had before. So let's think about how many evens I have. A 2 is an even, so I get 2. 4 is even, so I have 1, 2, 3. And then in the next row I have 1, 2, 3. And then in the next row I have 1, 2, 3. And then in the next row I have 1, 2, 3. So it looks like I have 3 evens in every row, right? Does that make sense? And how many rows do I have? Well, 6 rows. So it looks to me like there's 18 out of the 36 are even. Does anybody have a question about that? Do you see what I'm doing? Say that again.
I'm confused. So for the row that the first number is 4.
Yeah.
Wouldn't there be 4 even? 4, 6, 8, 10?
What do you mean by that?
Because there's number 4, number 6, number 8, number 10. Or am I looking at?
No, look at the very first row. So I'm looking at, can you see my cursor?
Yeah.
I'm saying let's look at the first row. The first row I have an even at 2,
Okay.
4, and 6.
Okay.
Then in the next row I have an even at 4, 6, and 8.
I see. Okay.
Yeah.
I see what I did.
You sure?
Yeah.
All right. So if there's anybody's confused by this, let me say this again. I'm starting at 2 and then I'm reading across. I have 1 at 2 and 4 are evens. And then 6 is evens. So it looks to me like I have 18 options for even. And that shouldn't shock me, because we would imagine the symmetry tells us there's just as many evens as odds, right? But then your intuition might say, well, I don't know, Grady, there was more 7s than anything you said. And that's correct. But then there's the least amount of 2s and 12s as anything, right? So it actually balances out. So if we just trust our initial count, then this looks to us that this should be 18 over 36. And so if we do this, we get 20 over 36. And if we divide everything by 4, we get 5/9, we think. So we could just trust our gut that 5/9 is the probability of a 3 and the probability, excuse me, or the probability of an even. Now, let's go back to our thing and let's see if we can count all these at the same time. So if we go back to our picture, we'll see if we have any errors. So we have a probability of a 3 and an even. So in the first row, I have 1, 2, 3, 4, right? So I have 4 in the first row. In the second row, I have 1, 2, 3, 4, right? So I have 4 in the second row. In the third row, I have 1, 2, 3 now. And then in the fourth row, I have 1, 2, 3. And so being that the numbers are going to count, the first 2 rows, I'm going to have 4. So there's 4 times 2, which is 8. And then in the next 4 rows, I have 3. So I have 8 and 12, which is 20. So we do see, if we go back, that here, even though I didn't want to count them at first, if I do count them up the long way, I get 20 out of the 36, which of course is 5/9. So they again check. Now, the beauty of axiom 3 is it's telling us not just that we should verify it works, it's telling us that it has to work. If we would have got a different number, then guess what? We did something wrong. We understanding that? Well, this is fun, except it's not. Or is it? I like this kind of stuff. You know, the weird thing, I have a friend, and she's in high school now, but, well, I shouldn't say, let me rephrase that. That sounds creepy. I have a friend whose kid is in high school now. But a few years back when she was like 12, 13 years old, actually, she was even younger than that. I lied. This was probably more like, she was probably about 10. It's funny how studying something like dice is much more difficult in a position you guys are at because you want to overthink it. And so I remember giving this to her. I said, because we used to play this game, my friends and I, we called it fake craps, where we played this game where you put $1 down and you roll, and it's kind of like craps. And I always laughed because like the rules were set up in such a way that it was just like there was no skill involved. It's just luck. And she was trying to understand if someone could win. And I said, well, listen, just write it out. I said, go upstairs, get a sheet of paper and write out everything that can happen on a roll of dice. And then I said, now count, what do you think's more likely? And it's funny because we have such a hard time thinking about it because we want to overcomplicate things when we're at this age, I think, when we're in school, I think. But if you just go back to this thing and you ask yourself, what's most likely? Well, you ask yourself, what are the most of? There's more 7s on this chart than anything else. And so naturally, then we would imagine that 7 is more likely than any other number. And then also we say, oh, okay, well, there's more, the number that shows up the least is 2 or 12. And so we would say that those are the least likely roll. So sometimes instead of thinking about all these fancy words and all the algebra and the scary math that you're taught, sometimes it's nice to pretend you're just like a 10-year-old. And you're thinking of things not from a higher perspective, but from a lower perspective, if you almost want to dumb it down for yourself. Now, of course, you're saying, you go and say that, O'Grady, after you wrote all that scary crap down. And I said, this is true. I did write a bunch of scary crap down. But at some point, you have to be able to make a connection between the intuitive stuff and the scary stuff. All right. So there is a payoff for this scary stuff. So we're going to state that in a minute. Before we do that, though, does anybody have a question? Okay. So what's the payoff? So let's phrase it like this. The question you might, so what you could say right now is, okay, O'Grady, you made a big deal about these axioms, and then you went and gave us these examples that look just like the stuff we did with classical probability, which is true, I did. But that was only to hopefully try to reinforce these ideas to you. But now what we can do is we can say, okay, we can extend these ideas now to a more general scenario. So here is what we want to say about that. So with the axioms on our side, we can generalize the types of problems we can solve. And even make new definitions. So let's look at an example. And this one is going to be similar to a homework problem. So magician. That's what magicians like to do. Designs a die that is unfair. How is it unfair? It's unfair in the following way. It is twice as likely to roll a 3 or a 5 than 1, 2, 4, and 6. Let's determine the probability. You roll a 2.
Quick question.
Yes.
How do you make an unfair die?
Oh, I mean, you asking me how to make one?
Yeah, I'm like,
Actually, not hard. People have been
weighted or what?
you put, yeah, lots of tricks people do. They might drill holes in it. They might use different materials. There's a whole plethora of info on how to do that. People have been trying to beat casinos for years with that kind of stuff. Yeah, there's lots of tricks. Maybe you make the material, the density of the materials not uniform is one way of doing it. Some people drill holes. There's lots of things people can do.
Gotcha.
Make sense?
Yep.
Okay, so how can we reason the probability roll 2? Well, if we just had sort of our classic probability, we'd have a little more work to do. So here's what we can sort of, one way we can deduce it. I'm not saying it's the only way. Here's one way though. So we need to do some reasoning. So let's let how about we let P? Well, maybe P is a bad letter because I'm going to use P for something else. So let let's use W. So let W equal the probability of, so we can use shorthand. Well, we'll write it out once. So we'll say the probability we roll a 2. And so let's denote this as P of 2. And let's not forget that this is the same thing. Oh, excuse me. Let me let's note that under our assumptions, this is the same thing as the probability of rolling a 1, the probability of rolling a 2, the probability of a 4, and the probability of a 6. Then 3W has to be the probability that we get a 3 and the probability that we get a 5. Because I said it's 3 times as likely. Yeah? No? Say that again?
You said twice, not third. You said it was twice as likely.
Oh, I said twice? Oh, I'm sorry. Then, yeah, I'm wrong. Thank you. So it'd be 2. Thank you for paying attention. So if I do this, this is correct then. Would you agree? Yeah. Okay, so by our axioms, what do we know? The axiom 3 says that the probability of 1 plus the probability of rolling a 2 all the way up to the probability of rolling a 6, this has to equal 1. And so what this tells us then is this tells us that W plus W plus 2W plus W plus 2W, so that's 1, 2, 3, 4, 5, and then lastly W, that all has to equal 1. And so what we've deduced is that we have 2 and 2 is 4, 4 and 4 is 8, so we get 8W equals 1, or W equals 1/8. So we have a 1 in 8 chance of rolling a 2. Does that make sense? Or does anybody have a question, I guess is a better way of saying it. Now, I did take some assumptions here. I assumed that 3 and 5 had the same likelihood, and that likelihood was twice as much as the likelihood of the other numbers. And then, of course, you know, you could get into this philosophical question of, well, how do I guarantee that created my dice this? Well, I'm not saying that, we're assuming that the dice is created this way.
But Grady, I'm a little confused on it. Can you go through it one more time?
Yeah, so let's go back to the problem. The problem says I have a dice, and instead of all 6 things being the same likelihood, we're assuming that to get a 1, 2, a 4, or 6 is one probability, and to get a 3 or a 5 is another probability. Now, I don't know what those ones are a priori or in the beginning, but I do know how they're related. They're related that 2 times the probability of getting, say, for example, rolling a 2 is the probability of getting a 3 or a 5. So I don't know what the numbers are, so I have to reason them. So I start by giving it an unknown name. If there's something I don't know what it is, I'm going to give it a name. I'm going to call it W. I don't know why I use W. I really don't. Just came in my head. So I'm going to say the probability we roll a 2 is W. Now, by the setup of the problem, that means the probability that we roll 1, or the probability we roll a 4, or the probability that we roll a 6, those are all equal to W, whatever it is. Now, the assumption of the problem also said that it's twice as likely to roll a 3 or a 5. So that means that 2 times W would be the likelihood that I roll a 3 and the likelihood that I roll a 5. So then all that's left for me to do is to deduce what that W is. And the only reason I'm able to deduce what it is because I know that I have to roll one of the 6 numbers, right? And since they're all mutually exclusive, I can't roll a 2 and a 5 at the same time. That means the probability of each one of them has to add up to the total probability, which is 1. So then I'm just plugging in what these unknown numbers are. So the way you might want to think about it is the probability of getting a 1 is W. The probability of 2 is a W. The probability of 3 is 2W. You know, maybe if I filled these in, it might be a little more clear. I'm not quite sure. So maybe I'll help. Maybe I'll do this for you. And this might help a little bit. So this would be the probability I roll a 3. This would be the probability I roll a 4. This would be the probability I roll a 5, and then the probability I roll a 6. And these all have to add up to 1. So all I'm doing is I'm just writing down the corresponding probability underneath. So this is a little scary for a lot of us because it's algebra. And then I just add all these up. So these are all like terms. I have 1 and 1 is 2, 4, 5, 7, 8. So I have 8W equals 1. And so if I divide through by 8, I get that the probability is 1/8. And you can check that your work is correct because that means you take 1/8 and then you add it to 1/8. That's 2/8. And then the rest of them have to be, excuse me. Well, I sort of lied. 4 numbers would have probability 1/8, and then 2 would have probabilities 2/8. So if you add that up, you get 8/8. Maybe, yes. Does it work? Does it check? Yeah, so you get 4/8 and 4/8, which is 1. This is a much more difficult problem. Yeah. Damn reasoning. Doesn't it suck when your brain has to work? Why would they want us to make our brains work? So look, most of us, it's going to take some time for you to think about this. But the moral you want to take from this problem, even if the symbols in algebra are scaring you right now, is the only way we were able to deduce this solution was that we relied on one of our axioms. Does that make sense? So those axioms, they give us sort of the tool to answer this question. Now you might say, well, how do we know the question's correct if you just use some weird thing you're calling an axiom? Well, because I know that if I took a dice that actually had these properties and I did the experiment a bunch of times, this is what would happen. Now you might say, well, how would you do that? And I say, well, look, I already showed you the experiment with regular dice last week. I did it on the computer. I didn't make it up. Hopefully that convinced you. You know, we have a few minutes left, and so we don't write scary stuff down. Let's look at another thing that I can show you. Talk about convincing you. You know, sometimes students say, what do you mean? You know, how? So I'm going to show you this. I'm going to flip a coin 50,000 times right now. I'm going to flip it. Here, I'm going to flip a coin 50,000 times. And notice how many heads I got. I got 24,000 heads and 25,000 change in tails. So that's almost 50-50 split. Now, instead of doing it 50,000 times, what if I did it 500,000 times? Now I'm going to flip a coin 500,000 times. You'll see now, look at how evenly the heads and tails are split. If I flip the coin 500,000 times, I got 250,082 heads. I mean, this is, look at it's almost 50-50 split. In fact, if I round, it's a half and half. Like, think about order of magnitude. Have you ever thought about the order of magnitude in things? Like, for example, if you had $250,000, would you be worried if you gave me 82? I don't think you would. You'd make that up in interest in the bank in 3 days. So let's play the game again. I run I do the experiment again. This time, 49% of the time, if I round it up, it's 50% of my tosses were heads. Now, I can concoct an experiment where I had an unfair coin. You can go to the magic store and buy a coin that will land heads 20% of the time. And then you could see the same thing. Anyhow, listen, hopefully you guys will go home and think about this stuff. I'm not saying it was the easiest, especially the last couple things. Please look at the homework. If you have questions, email me. We could talk about them. And if you don't have questions, then I thank you, and I will see you soon. All right, guys, thanks a lot. Take care. Have a good weekend if I don't see you.
Thank you. See you.
Bye, guys. Thank you. Bye, Felicia, as the kids say.